All right, I hope you guys are having a happy Easter, first of all. And today we're going to be talking about chapter 6. So we just finished chapter 5, and now we're moving on to chapter 6, section 1, and it's going to be the area between curves. So when we're looking at this section, when it says area between curves, it means we're looking at this upper curve here. They label this one as f of x for the upper curve and the lower curve as g of x. So instead of just finding that value in correspondence to the x-axis, we're going to be looking at how do we find this area in between. And you can actually notice that if we subtract the difference, so f of x minus g of x, because right now f of x gives the region of everything below. So if you subtract that difference, then you end up with the area between the two curves. So this is what it looks like visually. We have f of x is from this point to this point. And remember, when you're below the x-axis, it's a negative area. So if we subtract a negative g of x, we're still ending up with the area of the entire region. So we're subtracting this area down here, and we get from this point all the way down to this point. So that's how you would calculate the area between the two curves. And right now they're looking at it as Riemann sums. So that's just looking at the rectangles, and we know if we take this limit, then it's eventually going to approach our exact value. So hopefully that makes sense so far. So again, just to repeat, we're taking f of x, so from this point to this point, and then we have minus g of x is from this point to this point, and the difference between the two values is going to be from here to here. All right. So continuing on, they give a nice animation to show. So first it says divide the interval a to b into n subintervals of equal width of delta x. Continuing on, so we're picking a point xi, making our rectangles. The width of each of the rectangles is at delta x, and you can use that to approximate the region in between. Okay, so continuing on, so if we take infinitely many rectangles, we're going to eventually, so in other words, taking the limit as n goes to infinity, n is the amount of rectangles you have. The more rectangles you have, the more exact this approximation is going to be. So we're pretty much solving it the same way, and we know we can rewrite this as an integral, and it makes our lives a lot easier. So we're looking at a equals, so the area is equivalent to the integral from a to b. That was a closed interval, so we're looking from a to b. We're taking the top function minus whatever the bottom function is. So the trickiest part, I think, for this section is to be able to figure out what the top function is and what the bottom function is. There's little tricks that you probably learned throughout the years of which one's going to be the one that's on top, but when in doubt, you can always graph it on your calculator. All right. So then it shows how you can break this up into two different integrals if you wanted to. So it gives you f of x, and we know if we subtract this area down here, we get the area in between. Alright, so for example 1, it says find the area of the region bounded above by y equals e to the x, bounded below by y equals x. So they tell you which one is the top function, which one's the bottom. So we know we're going to be taking e to the x minus x. And so we're looking between 0 and 1. So we know we're going to be integrating from 0 to 1 and subtracting the difference between those two functions. Then we just integrate it. So e to the x, the integral of e to the x just stays e to the x. Remember, for integration, we're adding 1 to the exponent and dividing by that new power. And then we're looking from 0 to 1. So we plug in all our values for 1. We plug in all our values for 0. So we end up with e minus 1/2. That was plugging in 1. And then when you plug in 0 everywhere, you just end up with subtracting 1. Okay? And then that's equal to e minus 1.5. And they show it down here below. So again, we have that top function, we're subtracting the lower function, and we get what's in between. And they have a couple different animations throughout this section, which makes it nice to visualize. Alright. So again, it gives another nice little visual example of everything. Okay, so going to example 2. Find the area of the region enclosed by the parabola y equals x squared and y equals 2x minus x squared. So first we have to figure out what the top function is and what the bottom function is. So we know that y equals x squared. That's going to be a quadratic function. So you're going to have a type of parabola. So it's going to be a U-shape, and because out in front we have positive for that coefficient, so we know it's going to look like a U. Alright, so looking over in this function, we know it's going to be flipped over, so it's going to look like a hill or a mountain, an upside down U, because it has that minus sign for that leading coefficient. So if you put those two functions together, you know that this function right here is going to be on top. So that's kind of how I look at it. I start by looking at the leading coefficients and see if I can easily think about what it's going to look like in my head. And if you can't visualize that, maybe revisit some of the basics in graphing, quadratics, and different functions like e to the x. But yeah, you can always use your calculator, so don't be afraid of that. So we first find the points of intersection. So this point is a little tricky. Well, this example is a little more involved because you have to find the intersection point. So the intersection point, remember, is the point in which these two functions are going to be equivalent to each other because they're going to have the same values at those points. So if we want to find the intersection points, all we have to do is equate these two functions. So that's how they get x squared equals 2x minus x. This is pretty easy to solve for combined like terms. So we get 2x squared minus 2x equals 0. And because we have something equal to 0, we can factor things out. And we're left with x is either equal to 0 or it's equal to 1. So we have the points of intersection. So they give you the x values. To find the y values, it's really simple. You just plug it back into the original equation. And it doesn't matter which one you plug it back into because they're equal at those points. So we have the point 0, 0, and we have the point 1, 1. So we see from figure 6, I think that might be down here, yep, that the top boundaries are this one, which if you didn't notice it right away, they have the graph down below. Okay, so again, looking at this, the area of a typical rectangle is this function right here. Okay, so we're basically integrating from 0 to 1 because again, we're looking at the x values. Sometimes you'll find that it's easier to look at the y values and use y as a function of x instead of vice versa. So either way would work. You just have to make sure you're picking the right values for your bounds. So we're going to use the x values because it's pretty easy to see we're looking from 0 to 1. And so that means since we're looking at x values, we want x's all the way through here. I hope that makes sense. So we'll look at other examples that have the opposite. So we have a equals from 0 to 1, and they have the top function first, and then they're subtracting the bottom function. They already combine like terms right here. And then they're integrating. So they ended up factoring a 2 out, which you can totally do, or you can leave that 2 in. Doesn't matter, it doesn't make a difference. You get the same answer. So they factored the 2 out, and so they're adding 1 to the exponent, dividing by 2, adding 1 to the exponent, so it's x to the third over 3. You just have to remember to redistribute that 2 back into everything. So when you're looking from 0 to 1, you plug in a 1 everywhere. Then you subtract, plugging in a 0 everywhere, which is just 0. And you have to redistribute that 2. So that's how they end up with 1/3. All right. So again, how did they get to 2x minus 2x squared? Well, they took 2x minus x squared minus another x squared. That's how they got that minus 2x squared. All right. And then again, they have a nice little animation of everything. Yay! So I hope this is making sense so far. So sometimes they give you the bounds, and sometimes they'll have you find the bounds, which would just be the intersection points. But again, like our previous example, they actually didn't end up, sometimes your function doesn't end up intersecting, so that's why they would give you the bounds for it. So example 3, we'll look at real quick. Find the approximate area of the region bounded between the curves x over radical x squared plus 1 and y equals x to the fourth minus x. So again, they're finding the intersection points. So you would have to solve a problem like this, but it's very difficult to solve this exactly. In fact, it's impossible. So this is an example where instead you use a graphing device to approximate the area. So that would be something that you would use Desmos for, and it'll make it a little bit easier. So you can use, or your graphing calculator. So you use your graphing calculator to find those intersection points, and then you solve in this way. Okay, so this one's a little more difficult, not something you would always run into. You have to use U substitution, which we know how to do everything and we know how to solve it, but it's a little more tedious for this example because you're trying to find the intersection points using your calculator, and then you're doing U substitution and all that stuff. But the key to this problem is you realize that you can split this up into 2 different integrals. So you can use U substitution for this first integral, and then just regular substitution with this, regular integration with this second integral right here. Alright, so that's how you would solve a problem like that. Alright, so continuing on with everything, I forgot to mention real quick that the bounds, notice the bounds are switched on this. They switched the bounds here because we're using U substitution. So that's why instead of being from 0 to 1.18, it's 1 to 2.39 because they're plugging in the X values into U. Okay, so I think that sums up that example. It's pretty straightforward. Other than that, you're just using U substitution, and then over here you are doing normal integration and then subtracting the differences between the two. I think what trips people up the most, especially when it's examples like this where you're doing two different integrals, you have to make sure you're subtracting the entire thing. So you're using parentheses and distributing that negative value. All right. So let's see. So this can be applied to velocity as well. So again, you're doing the same thing. Let's see, what other example do I want to look at? Oh, this is interesting because it's talking about measles, so a nice little disease example. So it shows how the disease develops in an individual with no immunity after measles virus spread into the bloodstream from the respiratory tract. Okay, so you can estimate what that curve is going to be. So they give the curve. They give what they use to model the curve. So it's this function right here. And this actually isn't too bad to integrate because you can just distribute everything. Remember, you can use algebra in order to solve integrals. So if you see something and you don't know how to integrate it right away and U substitution doesn't look like it's going to be that helpful, you can just distribute everything out. And this is actually really easy to distribute because you have two binomials here and then you're just multiplying by minus t. And then it's really easy to integrate. So if infectiousness begins on day 1, so they have day 1, T1 is equal to 10. Oh, sorry. So they're saying they're starting at, they want to look at day 10 to day 18. Okay, so they have T sub 1 is equal to 10, and T sub 2 is equal to 18. And they want to see what are the corresponding concentration levels of infected cells. Well, to figure this out, they find the points. So to find those points, right, they're looking at T1, T2, T1 is 10, T2 is 18. To find those point values for it, all they have to do is plug it into the original function. So infectiousness begins when the concentration reaches F10. So they're just plugging in T1, and they're getting an output of 1,210 cells per milliliter. And it ends when the concentration is at F18. So like I said before, all they're doing is plugging in those values into the original function. So they're plugging in 10 into this function up here, and 18 into that function. Okay. So then they're looking at the line P1 to P2 to try to evaluate what this function is going to be, this line right here. Because once we know what this line is equal to, and So y equals, we know it's linear, so y equals mx plus b, right? We need a slope and we need a point to figure out what that equation is. And then you can use point slope formula to get the equation of this line. And you already know the equation of the top line, then you can subtract the two values. So looking through, they have the 2 points. They find the slope between the 2 points. So again, we're taking the y values over the x values, and we get minus 23. So the equation, you can pick any point. They're using point slope form. They just have n's and t's instead of y's and x's. So in this case, n is representing y and t is representing x. So we have y minus the y value equals the slope times the x, the difference between the x values. So that again is just using point slope formula. And then they solve it so that it's in the form y equals mx plus b. So they distributed that minus 23 to everything, and then brought over the minus 1,210 by adding it to both sides. So then you can finally find the area between the two curves. So we're looking from 10 to 18. We know that because it's our x values given. We have f at t. That was our original function. So our original function, going back up. So they, instead of writing it all out, they just put f at t. But they're going to be plugging this in eventually. So they skipped a lot of steps in between. And then they're subtracting this bottom curve, which they solve for. So this linear equation. So they're subtracting that bottom curve. And then to get from this step to this step, let me make it bigger for you guys. They are combining like terms. So first they distributed everything like I said before. So when you take this equation and distribute everything all out and combine like terms, so the only like term they're combining is going to be plus 23, because again you distribute that negative. So they're going to be adding 23t to whatever the t value was. Oh, so they have 21t, so they haven't combined like terms yet. So they get minus t cubed plus 20t squared plus 21t when they distribute everything, and then they distributed that negative out to get to this part right here. And they're almost done. They're just going to combine like terms. So that's how they got from this top step to this bottom step. And then this is pretty easy to integrate because we only have plus and minus in between. So we can integrate each part by adding 1 to the exponent and dividing by that power. So that's how they got from this step up here to this step down here. And they're evaluating from 10 to 18, so when t is 10 and when t is 18. So they just plug in 18 everywhere. So everywhere you see a t, you plug in an 18 and you find that value. And it looks like they found the value to be minus 6,156. And then you subtract the value of plugging in a 10 everywhere. So everywhere you see a t, you plug in a 10. So they're subtracting minus 8,033 and 1/3. And then that gives you 1,877. And that's in cells per milliliter times days. So they found the level of infectiousness for the patients. Okay, so maybe we could do a do a project with that with the coronavirus. All right, moving on. So they have these values here. Let's see. Okay, so sometimes you have a point of intersection in the middle, so it might be helpful to break these into two different areas. And then notice how this is also symmetric. So since this is symmetric, this is right in the middle, this intersection point. So you can just find the area of the first one and multiply it by 2 to get your answer. Either that, or you can add those two integrals together. Okay, so hopefully that makes sense as well. So you have different options. You just have to visualize it and think of the goal of the problem, and the goal is to find the area, the total area. So you can break it into as many parts as you want. You just have to make sure that you're getting all of the area together. All right. So when they find the intersection points, they're equating sine and cosine. So you can figure out when sine and cosine are equal to each other by looking at the unit circle. So actually, let's pull up the unit circle. Unit circle. And when you pull up the unit circle, we can see, well, when we are at, oh, I want a different one. Let's see. This one's a little easier to read. Okay, yeah. So when we're at 45 degrees, or pi over 4, we have sine and cosine are equal to each other. So when we equate the two, we get x equals pi over 4. And we're looking from 0 to pi over 2. So they did a quick sketch. Okay, so first they start out from 0 to pi over 2. They're subtracting the difference between. And notice they're taking the absolute value of it, and it's a1 plus a2. Okay, so they split it up into those two different integrals because notice, so they have absolute value because notice that the top function switches halfway through. So we start off with having cosine at the top, and then we finish with having sine on the top. So in other words, down here, they have from 0 to pi over 4, they have cosine first. That's our top function minus our bottom function. Then for the rest of it, from pi over 4 to pi over 2, they have sine and then minus cosine. And then this is pretty easy to integrate. You just have to remember your rules. So to integrate cosine, it becomes sine. Integrating minus sine becomes positive cosine. Sine becomes minus cosine. And minus cosine becomes minus sine. And then again, plugging in those values, just making sure that you are distributing that negative. Notice how it's minus minus here, because they distributed the negative. Same over here, when they distributed the negative, everything became positive. And pi over 4, when you plug things in, it becomes 1 over radical 2. And then they just simplify and solve. So to simplify this, some people have difficulty simplifying this. But you're just combining it like you would normal fractions, right? So the denominator stays the same in everything. And then, so that's how they get their 2 radical 2. And then the minus 2 comes from this minus 1 and minus 1. Okay, so hopefully that helped. I'm going to leave it here for today. They have an animation showing you everything. But the rest of it is just going to be exercises. So for the next discussion post, I'm going to have you do some exercises. I know some people were saying they're